We're going to learn today. All right, 2-6, and I don't have anything put it up, so you have to do this in your notes. We're going to see today our first theorem, okay? And we're going to go back to the idea. If you guys remember, we had postulates. Basically, postulates were the foundation of geometry that we were agreed upon. And so we're going to have some starting facts that kind of gets the ball rolling, okay? And we also needed some definitions that we started with: lines, rays, and points and planes, and points, planes, and lines. We needed those three things to get the ball rolling to create other terms, which gave us rays and segments. He eventually created angles and that kind of stuff. And we started developing larger groupings of statements. Does that make sense? Okay, we started with three basic terms. That led to a fourth term, led to a fifth term, led to a sixth term, led to a large group of definitions. Okay, we start with a handful of postulates. Okay, and we start combining those postulates with definitions, and we're going to find out today that it creates our first what we call theorem. Okay, and then as we progress through the year, we'll take some of those theorems and combine them with other theorems and create new theorems. And basically taking these individual facts, putting them together. Okay, we started with a very simple set, but put them together and they develop bigger and better things. The analogy I used last period was, if I go to, a construction site and I throw down some 2x4s, box of nails, a hammer, some shingles, and some plywood, by themselves, they're just small components, right? But if I start putting them together, I can probably build something, right? Maybe I can make a roof, okay? I make something bigger and better. So that's kind of the idea that we're going to see happen today. We're going to develop our first theorem, and we're going to see then kind of the necessity or the application of theorems as well. So what I want you guys to write down is, well, let me do this. I kind of adjusted this last period and didn't fix it. All right, so the first thing there is it's a theorem. Okay, that's a definition up there. It says a conjecture or statement that you prove true. That's the definition for a theorem. All right, and you can see it that contrasts with what we talk about in regards to postulates. Because postulates, we know postulates cannot be proven, right? They have to be accepted facts. But a theorem, you should be able to walk through. You should be able to show me, tell me exactly why that statement is true. Okay. I'm not interested right now. I think the better you get at proofs, the quicker you'll understand and the easier it'll be to understand that, this statement cannot be proven. This statement has to be a postulate. Or this statement can be proven. This statement must be a theorem. I'm not really worried right now whether when we look at these things that if you can remember which ones are theorems and which ones are postulates. That's hopefully a goal. But I am interested in, and I do need you to know, the difference between the collective statements that are called theorems and the collective statements that are called postulates. Which ones you can prove and which ones you cannot prove. Okay? But ultimately, we use them or apply them in the same way. All right, they're going to be essentially our reason or potential reason when we work through a proof. Okay? The first one we come across, first theorem, is something we talked about earlier. We've used it already algebraic a little bit, and we'll continue to do that in this section. But the first theorem is, it says vertical angles are congruent. Vertical angles are congruent. Basically saying up there, angle 1 and angle 3, by definition, these are vertical. And 2 and 4, by definition, those are vertical. This theorem says if that's what you have, then the angles are congruent. Now, look at the way I wrote this statement, or I guess your textbook wrote this statement. And I told you early on in the process of dealing with properties or rules that your author, your textbook are going to provide you, I told you they're always going to be written as if-then statements. And then the textbook right away contradicts that. Okay? They do something differently. They do not write that as an if-then statement. And if they don't, that's okay, we should still be able to kind of reorganize it or restructure it as an if-then statement, keeping the same information. Okay, not bringing anything new in and not leaving anything out. Okay, would you guys agree that if I write that phrase, if two angles are vertical, then they are congruent? That's the exact same thing as vertical angles are congruent. Now, the reason I like to write it that way is because the next thing they're going to ask us to do is prove this theorem. Okay, and they're going to. I set it up for you. I've already given you kind of the structure for the proof. I've given you the given. I give you the proof. But you will maybe come to a point in your math career. It might be this year. It might be the end of course again. It might not be until you're a sophomore in college. I don't know when it's going to happen to you. But they're going to say, prove the vertical angle theorem. And they don't give you the setup. They don't give you the chart. They don't give you the given. They don't give you the proof. They don't give you the pictures. And you have to start from scratch with just the if-then statement. Okay? So I'll show you how you do this. It's pretty straightforward. But the if-then statement, the red part here, what do we call the red part? What was that vocabulary word? The hypothesis. The hypothesis turns into your given in your proof. Okay? So if the red becomes the given, what's the blue part become? That's the proof. Okay? That's the proof statement. So when we look at this in the next slide, we're going to have that phrase in our given, in our proof. Now, I'm going to copy this and go to the next slide. And I want us to compare. Okay, we're proving this vertical angle theorem statement. Now, here's the thing. That red statement, that red hypothesis is not exactly word for word or verbatim. It's not an identical match between what is written in red and what is written under the given statement, right? Because if I just write in my given statement, two angles are vertical, that's going to be really hard throughout my proof to talk about the angles. I need to be able to describe them. Okay? If none of you came in here with names, would it be hard for us to talk to each other and reference conversations and that kind of thing? And me to call on you and that kind of stuff? Okay? So we got to have names for two angles. So we choose 1 and 3 in this thing. Okay? If you wanted to use, letters or whatever, you wanted to use different numbers than 1 and 3, that's fine. But you need two angles, and you need the argument that they're vertical. Okay? We have to be able to reference something. We have to be able to talk about something. Okay? And it says they are congruent. Well, they is representing our two angles, right? The two angles that are represented in our given is this they are congruent. So 1 and 3 are congruent. Does that kind of make sense? All right? When we do a proof, and not many courses discuss this and talk about how to do this. They just make the assumption that we can look at it and make the connection. When you are providing an if-then statement, okay, that if-then statement is a general statement for all things that are discussed in that hypothesis. So this is discussing this situation for all sets of vertical angles. When we go through a proof, we need to make specifics. We need to be able to discuss one case or one scenario so that we can actually prove this. Does that make sense? I struggle with that. It makes sense to me, but I struggle to explain it. Okay? Hopefully that was good enough for you. All right, so we look at our given. Remember, we always write our given down, right? Okay? And this is kind of like yesterday, where we write our given down. We look at our vocabulary word here, right? Vertical angles is a vocabulary word, okay? That's, excuse me, that step that I gave you on Friday, that handout that said, look at your vocabulary word and determine what congruencies or kind of relationships that develop from those vocabulary words, you're going to write that down. So like when we call it midpoint, that gave us two things that should be equal, right? Two measurements that should be equal or two segments that should be congruent. When we saw the word bisect, a similar thing happens. We get two congruencies, or two segments that are congruent. When we see the word supplementary, that brings in some algebra, right? When I see supplementary, it allows me to say this angle plus this angle equals 180. So those are kind of algebraic facts, right? That those vocabulary words are bringing in. And that's what we're hoping for when we see a vocab word, is to bring in some algebraic facts, some relationship. When I look at the vocabulary word for vertical angles, and this is something that we have to do throughout all of mathematics, guys, is that even though this is a vocab word that we learned maybe September 12th, okay, and right now it's October 17th, we still have to know what that vocabulary word says, okay? And if we don't remember it word for word, we need to be able to find it, okay? So I searched through and found section 1.5, we identified vertical angles, what they were, okay? So there are two angles such that the sides of one angle are opposite rays to the sides of the other angle. And what that is, guys, is kind of like what we call an existence definition almost, okay? It just showed me how they show up. It just showed me how they're created. It doesn't give me a real nice characteristic, like this angle is equal to this angle, or these two angles add together equal 180 or 90 or something like that. Does that make sense? So it's kind of a bland definition in regards to what it provides us in our proof. This is one of the situations, it was like we saw it yesterday with linear pairs. It's one of the few vocabulary words that we're going to go through and see throughout the year that really don't lead us to anything right now. Okay? So, what is that vocab word? There's nothing I can do with that. Okay? But we go then in that handout that I gave you last Friday, we go to the next step, which says, what's your picture? And you should be able to determine some things from your picture. Okay? And this is going to be a little bit different than what we've done so far, because it's just the first time we've seen it. When I look at my picture, we should always be able to determine when two angles form our straight angle or our line. We should be able to look at angle 1 and angle 2 right there and automatically know that those two things form a linear pair, right? Does that make sense? So yesterday they gave it to us in words. They said angle 1 and angle 2 are a linear pair. Okay? Now they're just saying the exact same thing, but with a picture. Is that right? So yesterday, if you went back to your notes yesterday, if you look through your proof of yesterday, our first statement would have said, like, this angle, I think it was angle 1 and angle 2, are a linear pair. And then the next thing we said was because they're a linear pair, they are what to one another? Supplementary. Okay? So what we're going to write here in step number 2 is the exact same thing that we wrote yesterday. When you saw a linear pair yesterday, you said that those two angles described in that linear pair are supplementary. So here, angle 1 and angle 2 are again supplementary. Okay? So how did I know that? It's not the definition of supplementary, because the definition of supplementary means I'm going to bring in the number 180, right? I'm going to add some stuff together. So it's not that. It's not vertical angle. It's what I was looking at in the picture. Angle 1 and angle 2 are what to one another? As a group, they are a close linear pair. Okay? Now, the definition of linear pairs doesn't say anything about them being supplementary. The definition of linear pair is that they are two adjacent angles whose non-common sides form a straight line. Nothing in there said the word supplementary, right? But the linear pair postulate, okay, the linear pair postulate says if you have linear pairs, which is what 1 and 2 are, right? If you have a linear pair, then those two angles are supplementary. That's what's going on here. Okay, so my reasoning for saying that 1 and 2 are supplementary is the linear pair postulate. Which I'm just going to write down here what that linear pair postulate actually says. Says if two angles form a linear pair, then they are supplementary. All right, so guys, if you were to look back to yesterday's proof that we did, okay, that incorporated linear pairs in, I think the first one we did yesterday. The phrase linear pair showed up, and we wrote angle 1 and angle 2 are supplementary because of the linear pair postulate. The next thing we did is that when we seen supplementary, we then talked about what that meant for us, right? Okay. Now I'm going to kind of put that on the back burner because of the fact that we've really got this supplementary angle showing up twice. If I can say that about angle 1 and 2, Can't I say the same relationship about 2 and 3? Okay, so if you can say that about multiple things in your graph or your picture, go ahead and do that. All right? So angle 1 and 2 are supplementary, but so are 2 and 3. And that's the same reason. It's a linear pair postulate. Okay. Yesterday I told you if you get a cluster of statements, the first time you see that you have a linear pair and you use the linear pair postulate, you then say that those two angles are supplementary. And once you say that, then the next thing you say, because they're supplementary, that those two angles add for 180. So for us, look at this black statement. If angle 1 and angle 2 are supplementary, that should allow us to write the measure of angle 1 plus the measure of angle 2 equals what? 180. Okay? So that statement is the third statement in that cluster that we talked about yesterday. All right, we're just seeing that cluster kind of happening twice here for us. Because then with the red stuff, angle 2 and angle 3 are also supplementary. Can I write this? Does this make sense? All right, now how did I know if I had two angles that we stated were supplementary, and then I convert that into that algebra? How do I know I can do that? Good. The definition of supplementary angle says that two angles whose sum is 180. Reason number 3, definition of supplementary angle. All right, so what I like to do within proofs, and even just in general, when we're going through mathematics and we're trying to talk about the reason why we're doing something or a connection that we're trying to make, if there is kind of a link back to a course that we've already mastered, Algebra 1, we're all here because we passed Algebra 1, right? We passed it to a prerequisite of a C, all right? So we did okay in there, right? I like to go back to, okay, you understood this idea in Algebra 1. Let's see if we can recognize that the same idea is really happening here in geometry. So here's kind of what I'm talking about here. If I take in Algebra 1, you guys remember seeing, I got my y-axis, got my x-axis, okay, and maybe then I give you two lines. So let's say we've got that line right there, and maybe that line right there. Let me color these so we can talk about them a little bit easier. The red line, and we got the blue. Okay? So let's say, the blue one is called line 1, the red one is called line 2. Okay? And you graph these two things, and we wanted to see where they were equal. You remember doing that? Okay? And the graph was, okay, you can count over however many units in that direction and however many units in that direction, and these two lines are equal right there at that point, right? So you found that ordered pair, and that's where the two lines are the same. You did that graphically, and then the next day or maybe a couple days later you came back and said, okay, now that we can do that graphically, let's look at what line 1 was algebra said. Line 1, would you guys agree it's going to look like y equals, it's going to be some positive, so let's just say like, some arbitrary here, 3x, and then let's say that my y-intercept is plus 2. Remember doing something like that last year? And then the red one, maybe it's got a slope of, negative 2x. And maybe a y-intercept of positive 1. Okay? And we were asked then, okay, if that's the algebra, that's the set of equations for those lines, can we do a procedure, can we go through the analytical approach to determine what the ordered pair is without the graph? And here's the concept. If I'm trying to figure out where these two things are equal, right? These two lines are equal, okay? Essentially we're looking for the x value in which the y values are the same. So if I look at this point right there, would you guys agree that the y value of that point is on the red line, and it's on the blue line at the same time. Okay? So at this point, we are interested in essentially the y value of that point on the red line being the same as the y value of that point on the blue line. Okay, everybody? Means the y values are equal. So if these are the two equations that represent those two things, we're saying that at that point, that y value and that y value are the same, correct? If those two y values are the same, what's that tell you about these things here? Okay? They're the same as well. So last year you took 3x plus 2 is equal to negative 2x plus 1, right? And you went through and solved that. You guys remember doing that? All right? The idea was you said, well, y equals 3x plus 2. Well, if y is equal to 3x plus 2, let's come down here, and where I see y, pull it out and replace it or substitute it with what it was equal to of 3x plus 2, right? That make sense? We've done that substitution before. Let's go back to the proof that we're doing. That same situation is happening right now in front of us. We'll have x's and y's and that sort of thing. But do we have two equations where those two things are the same? That make sense to everybody? Okay, so in the algebra aspect, those would have been your y's, right? Those are the objects that are identical, or the same. So if those two things that I highlighted are the same, what can you do with these things? Okay? Okay, so I should be able to say that measure of angle 1 plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 3, right? And you told me that's substitution. Now, I'm just I'm losing my kind of order over here. We're trying number, but I go straight on it. I'm going over and up a little bit, right? So statement 4, substitution. All right, so that kind of validates or gets us back to talking about what we discussed yesterday towards the end of class. If we start developing algebra on the left-hand side in our statement, a way that's going to allow us to kind of move on and progress through our proof is either subtraction, maybe addition, okay, because it's really kind of the same thing, or substitution. And that's going to allow me to create new true facts. Does that make sense? In this case, we had to use substitution. But now, I've got algebra over here still, right? Still have some algebra over here. But what is nice about that blue statement? What do you recognize about that blue statement? Okay, angle 2, okay, that measurement is some number, right? So, again, going back to algebra, if you had like 2x plus 5 and x squared plus 5, do those 5s balance each other out? So they're balanced if they're there, but aren't they also balanced if they're gone? Okay, so let's get rid of them. All right, it's just a number hiding behind that symbol, and it's on both sides. Let's get rid of it. If I get rid of it, we're left with measure of angle 1 equals measure of angle 3, right? Does that make sense? When you got rid of it from both sides, getting rid of something, you use what operation? Subtraction. We did it from both sides, so it's subtraction property equality. All right, so now we get to this last statement, measure angle 1 equals measure angle 3. That's not exactly what we wanted to prove. So think about this. Measure of angle 1, using that symbol, we know that there's actually a number that we're trying to reference here, right? But that number, because of the symbols we're using here, that number should be attached to some angle, correct? Okay? So we're saying that this number here is the same as that number there. That means that the sizes are the same, correct? But they both come from shapes that are angles, right? So if the sizes are the same and the shapes are the same, we have congruency. That meets the definition of congruency. Same size, same shape. So we can then jump from equality straight to the fact that angle 1 is congruent to angle 3. Okay? The definition of congruency, abbreviate that way. Your textbook would say this, congruent angles have equal measures. Okay, which is kind of a phrase that can be read left to right or right to left. Okay, measures that are equal come from congruent angles, right? Does that make sense? Something that kind of is procedural is something you always do, okay, or you always can do. If I have equality, I can jump straight to congruency. If I have congruency, I can jump straight to equality, and the reasoning will always be definition of congruency. All right. And that then matches up to what we wanted to prove, right? Again, something that I didn't really set out to do in this problem. I didn't look at the proof and say, I need to pigeonhole myself into being able to get there. I didn't even think about that at all throughout the entire process, okay? It just kind of fell into our lap as we moved through and made connections, right? And that's what's going to happen probably 90% of the time when we do proofs, okay? Write everything down we know, and we start then using this idea of, you know, law of syllogism, law of attachment to kind of collectively create things, okay? So what do we say here? This theorem, this new statement, if you look at it, it's created by the clustering of a postulate, some kind of basic definition, supplementary angle, right? Okay. And if you think about that, supplementary angles, okay, that's a definition that is created by some simpler concepts. All this would kind of dwindle back down to the linear pair postulate and the definitions of the undefined terms of points, lines, and planes. Does that kind of make sense? All right, but we kind of put them together and build something a little bit bigger and a little bit better and a little bit more informative, and we get what we call the vertical angle theorem. Okay? What's the benefit of it? Every single problem that we do, guys, once we prove it, if I ever see that again, I don't have to go through the proof again. All right, now in class we might just for the practice and the recognition of it. But if I ever want to use, if I ever see now two angles are vertical and I want to say that they're congruent, I don't have to say these 6 steps. I know it's going to be true because of these 6 steps. Is that all right? So in the next slide, I want to show you the next slide real quick. We'll do another proof that's pretty straightforward, pretty simple, I think, in regards to comparing to what we just did. In this picture here, okay, in this proof, we're going to try to start off with angle 1 congruent to angle 4, and then prove that angle 2 is congruent to angle 3. Now, the way it's set up, it's got 5 steps in it. Okay, we might even be able to shorten that if you think about things correctly. All right, I think we can make it down to 4 steps ultimately. But if I didn't have the last theorem, because throughout this problem, guys, look at the board. We see angle 1 and angle 3, right? Are those vertical angles? We're going to want to say that they're congruent in this problem. But if I didn't have the theorem, the only way that I could do that is to go through the 6 steps that we just went through. Does that make sense? Look at 4 and 2. Are they vertical? We're going to need those. Okay? If I didn't have the theorem, I got to go through the 6 steps to show that 4 and 2 are congruent. So in this process, guys, in this proof, if I didn't have the vertical angles theorem, I would have 12 additional steps on top of the ones that are already up there that we need for the rest of the problem. Does that make sense? So this proof could be ultimately, I think 15 or 16 steps if we didn't have that vertical angles theorem. Okay? So these theorems allow us to kind of restate a fact without having to go through and prove that fact again. Okay? Throughout every proof we go through. And we could do that. Every time I see a homework problem, we could do that. Okay? All the proofs we did yesterday and the day before, those are facts that we have proven to always be true if given that situation. It's just that with those other ones we've done, and in the some that we're going to see here, even this one, we're going to prove this to be true all the time. But you're probably never ever going to see that picture again and be provided that given and proven information again inside another question. But we will be provided vertical angles at some point in other questions. So just because of how often we have to deal with vertical angles and how important they are to our work, we recognize that it should be written as a theorem. It should be a fact that we say it's always true, and we remember it, we retain it, and we can use it effectively. Okay, and it creates pretty much an efficiency type thing. Okay, is that all right, everybody? Don't shake your head too hard, Trey. Sounds like a baby rattle. All right, I'm going to just real quick hide these statements. Okay. So the first thing we want to do in proving this is write down our given, right? Angle 1 is congruent to angle 4. Given. Okay? Angle 1 is congruent to angle 4. When we start off with information that has congruency in it, it's going to be huge for this problem. It actually, by doing this, by making sure we go through our picture and adding stuff in, actually can save us a step in this problem if we think about it. We're going to go to my picture. I'm going to draw angle 1 and angle 4, and we'll make sure they're congruent. Okay. Now, the reason we do that, we're going to write a bunch of other congruencies in here, and if I left it blank, I would have to go through these 5 congruencies in the statement to argue my reasoning or to make a connection, where if I look at my picture, it's going to jump off the page to me. Okay? Based off of what we just learned with the vertical angle theorem, are there any other angles up there that you guys would maybe consider congruent? Anybody? 1 and 3 are congruent, right? Angle 1 congruent to angle 3. Okay? Now the reason is the vertical angles theorem, which says vertical angles are congruent, right? Vertical angles are congruent. However you want to write, I like, but there's kind of a reward and cost for learning the names of things. Okay, if I learn the name of something, it allows me to write my reason a little bit shorter, right? But the cost of that is that I might lose meaning of what's hidden behind that name. Okay, if all I ever learned about you guys were your names, we don't build a relationship with one another, right? Okay, but if I start learning more about you, okay, that's a good thing, okay? And I can start to maybe tailor class towards you. Learning the names of things can allow you to kind of just not know everything about what that phrase is saying. So if you're using this, that's fine. Like I said, it's fine. But make sure you know that it states that vertical angles are congruent. Okay? All right, so I now created a new congruency, right? So it's just like step 4 of that handout I gave you Friday. It says, if you create new congruencies or see them, go in your picture and draw them in. Okay? So now here's my thought. Here's what we got to pay attention to. 1 and 3 are now congruent, right? Because how many marks does 1 have in it? 1. And I cannot change that because it's already said somewhere else that 1 was congruent to something else, right? So because that has 1 mark in it, angle 3 has to have 1 mark in it. Okay? If, and this, I want you to see this, if I would say, well, 1 and 3 are at the new congruency, so I'll put 2 marks in 1 and 2 marks in 3. If I do that visually, that contradicts right there. That contradicts what we stated in 1 congruent to 4, doesn't it? Okay. We don't want to do something like that. If you have 1 mark here, 1 mark there, and I create a new congruency that incorporates one of those things, and that defines that that new mark in angle 3 has to have just 1 mark in it. Okay. So right there, hopefully maybe that's something that allows you to make a link between things. You now have 3 congruencies up there, right? You have angle 1 congruent to angle 4, and you have angle 1 congruent to angle 3. You have 3 things that are all the same, right? We've only identified 2 of them, 2 pairings in our statements over here. Is there a new third thing in here that we can say are congruent? Okay? Okay, so you're going to go off of, not looking at these three, you're going to say 4 and 2 are congruent because of what? Okay, so that's fine. We'll talk about this here in a moment, guys, because he answered differently than what my question was. But that's fine. Well, I just wanted you to look at 1, 4, and 3. And if 1, 4, and 3 were all congruent, and we have taught that 1 and 4 paired up and 1 and 3 paired up, shouldn't we also have a third statement that says 4 and 3 paired up? Looking at these three things here. If those three are all the same, we already said that the blue or the red ones are congruent. We said these two are congruent. The only two that we didn't say yet were congruent with 4 and 3. So that could be a new statement. Make sense, everybody? All right, so now we've got this idea. If we go Trey's route, we've got that idea, which is fine. And that's the thing about proof, guys. Is, you know, one route might be better than the other, might yield the same result, might be quicker, whatever, okay? The idea, though, is that what I'm about to come up with, the next statement we make, has to be in statement number 4 or statement number 5 because of what is already set up here, okay? So the statement that I make here is going to be what we call a dependent statement because it depends on knowing the facts that came above it, all right? And I'm just going to try to walk you through this maybe step by step first. Look at these two. All right, and this is the idea, this is the concept that you want to go through. If you start, so I'm trying to give you guys kind of visual cues that help you understand how to navigate some proofs. One visual cue was, if I start yesterday, we said we start doing some algebra over here. Maybe we want to use try addition, try subtraction, see if we can use substitution. So those are kind of narrowing your focus on some approaches. When you start writing a bunch of congruencies, 2 or 3 or 4 congruencies, you probably are writing them down because the transitive property is going to be present. Because we can make a linkage between 2 congruencies to develop a third one. Does that make sense, everybody? And what we'd be looking for if we're going to use the transitive property is a common term in 2 of these statements. Okay? Do we see how angle 1 is common in those 2? Now, I'm going to write this way. I'm going to say, and you don't have to do this, but I think it's a good visual to see. Actually, I'm going to flip the first one around. I'm going to write the first one as angle 4 congruent to angle 1. Is that fair to do? And then that second one says angle 1 is congruent to angle 3. Can you see that if angle 4 is the same as angle 1, but angle 1 is the same as angle 3, what's that tell you about 4 compared to 3? Okay? Angle 4 is congruent to angle 3. And I want to write that in a different color because I have to go green. Angle 4 is congruent to angle 3. Now the idea is this is an A, then B, and this is the same B, and then C, right? So if A is congruent to B and B is congruent to C, then A is congruent to C. What phrase was that? What property? Close. It's transitive, okay? Because of how we go through that kind of linear progression, if you said substitution, I'm not going to say no. I'm not going to say it's absolutely wrong because you're saying, okay, if 4 and 1 are the same, I'm going to come down here and replace that 1 with 4, right? So substitution, I don't think is a wrong answer. But what they're looking for here is traditionally it's transitive. But again, I would agree with substitution. Okay. Now, why did I write that in green? I want that to be in green because that is what we call a dependent statement. Meaning, it cannot come in my proof. It cannot be written in my proof until I have what is in that red box written down in my proof. Okay? It depends on knowing that that red box set of facts are true, and then this green one is a conclusion from that. Does that make sense to everybody? So this green one cannot go up here. It cannot be one of my first statements. It can't go here in the middle of these 2. Okay? It has to come after. Well, if it has to come after, could I do this? Is that after? Okay. So your neighbor might have that. Does that make sense to everybody? Okay. Where you might have the green one come after the blue one. It doesn't matter because this one is dependent on it, just these two. This one is independent of anything right now. Okay, I think that was a 2, right? 4 Corinthians 2? Yeah. That one is independent because it came from our picture, right? And we haven't used it yet. All right? But now what I want you guys to look at, now that we said 4 is congruent to 3, let's look at these. Let's pair these up. Can I go, maybe 3 goes to 4, but 4 goes to 2? Does that make sense? So I always try to take that common term and put that in the middle of my phrase when I start stating it. 3 to 4, 4 goes to 2. So my new argument is, okay, 3 congruent to 2, right? Or if you want to write it as, you're wanting to write it as 2 congruent to 3, but those are, the symmetric property says that those are the same, right? What reason is that? What logic? Because I can go from 3 to 4, but 4 goes to 2. Okay, substitution again will be okay, but what are they looking for? They're really looking for transit. When they want substitution, they're going to do more of like directly pull something out and directly replace it with something. I see what you're saying with transit property, and I've always thought the transit property is essentially a substitution process, which is fine. Now here's the thing, guys. I don't really need maybe all those steps. Okay, let's say this. Let's say that your neighbor, let's say they didn't do this green one. So they did this. Okay, and to be honest with you, because these are the same reason, do I need to rewrite that reason for it? No. Okay, so that can maybe shorten it as well. But let's think about this. If I'm putting things in my picture, if I'm adding things to my picture, and we've done that over here, we have 4 objects, and we're saying that they're all the same, right? And I talked about this with you guys earlier when we did transit property initially, is that if we have all the same grade in this class, I can go in the progress book, take any 2 grades out, and compare them and say that any 2 are the same, right? So it doesn't matter in the transit property that we've got 3 objects or 4 objects or 5 objects. When I have a cluster of objects, a cluster of things that are all the same, I can pick out any 2 that I want. Well, these 4 are all the same. Let's pick out any 2 that I want. Well, the 2 that I want are defined right there. Can I pick out 2 and 3 and say if they are congruent? Does that make sense to everybody? I could have made the jump right away that angle 2 is congruent to angle 3. Now here's the reason. Look at these. And it's going to be kind of hard to maybe bounce around, but look at angle 1. Since angle 1 is the same as 4, right? Angle 1 is the same as 4. My tablet's kind of dying here. There we go. 1 is the same as 4. But now come down here. 4 is the same as 2, right? Okay? Actually, maybe that's not the best way to think it. Let's do it this way. I'm just trying to see the link. Yeah, go ahead. 1 is the same as 4. And then 1 is the same as 4, and then 1 is the same as 3. So 3 is the same as 4. So 3, okay, so 3 and 4 are the same. So there you keep 3 and 4 the same. And 4 is vertical, 2 is the same. Yep. So you kind of, there's a congruency here that we maybe don't write down, but 4 is the same as 3, and down here, well, 4 was the same as 2. So that allows me to say that those 2, 3, and 2 are the same. Okay? If you want to do this, that's fine. But I think you see it's kind of easier to write down everything and be detailed so that you don't get people lost, right? But you could write 3s and 4 as being transit property. It's actually using it twice and be done with that proof. So that's kind of the nice thing I like about geometry, but it's also the thing that I hate is that we could come in here kind of theoretically have one proof and have 6, 7 different ways of doing it, and they'll all be okay. And that's the thing. Okay, can we talk about all of them being okay in 45 minutes? I don't know. Okay. So it's just something to kind of wrap your head around. No homework this evening. See ya. Have a great day.